another video in quantum mechanics. Already in the last two videos we have shown what is a matter wave and the quantity responsible for a matter wave. We discussed that a periodic variation of matter wave makes up a periodic variation of wave function makes up a matter wave, and so in this video we'll talk about wave function associated with matter wave. This is part 1. In the next video we'll take more account of the wave function. So let's proceed. First question is, what is a wave function? And wave function is not a unfamiliar thing for us. It's simply a mathematical entity to represent a matter wave, and this is also found in case of our classical physics problem, like those in waves and sound, where we put a representation like y equal s sine theta, where this kind of expression represents a wave function, and where we see that where this y is displacement is representing the wave function. However, the wave function for a matter wave is not the same as in case of a sound wave. It's simply a complex kind of thing, and we have to deal with it very carefully. So let's first think what the physically a wave function can represent. That is the physical interpretation of a wave function. As we have come to know that the wave function is a complex quantity, and the modular square of it has only a meaning, that the psi has no physical meaning, and it has only meaning when you talk about the modular square of it. To be more precise, as in the last video, where we said that a matter wave is a wave of probability, so definitely the wave function is related with probability. To understand it, we started equation 1, where we saw that this psi modular square dV is proportional to rho, representing the fact that this quantity is proportional to probability density. So definitely we can now define what actually this psi mathematical represents. If we consider the equation 1, we see that this is nothing but the probability of finding a particle within the volume element dV. Now removing this in proportionality sign, we put an equal sign here, and we find that psi modular square dV is equal to n modular square rho function over nt dV. Now this proportionality constant n modular square is nothing but simply the normalization constant, which will take care of it in a later course of time. And if you integrate equation 2 for over a whole space, then we'll find that equation 2 becomes like this, and since the probability for over whole space is equal to 1, so in that case we'll find that this psi modular square, instead of dv we're writing dx dy dz, we'll find this rho dv, and thus we see that this psi modular square dv is equal to 1, since the total probability of a whole space is 1, the right hand side is 1. And one thing we must remember, that here we have put the normalization constant square is equal to 1, which however sometimes may not be equal to 1. In that case we have to find it out from this condition number 6. And one more thing, or the modification we can bring in equation 6, is that instead of minus infinity to plus infinity, we can put some finite volume v1 and v2 to express it, and in that case where simply the infinity kind of things goes away and the finite things v1 v2 is replaced by. This equation 6 or 7 simply represents the wave function in a three-dimensional space. If you take a one-dimensional case where this dv will no longer exist, in that case we'll simply have a line element. In that case this expression 6 will turn into this psi modular square dx, where dx is a line element, and in that case in the same way we'll find that this psi modular square dx is equal to this. And important thing is that since in this case also the integration for the whole probability will equal to 1. So we conclude that the wave function as of its own has no physical meaning. It's a complex quantity, but if you take the molar square of it, it represents the probability density, and if you multiply this molar square with some volume element, then it represents the probability of finding a particle within that volume element. And this is what about we have shown here. Rho is simply probability density, but rho dV is probability of finding a particle within the volume element dV at a particular time t. And also, if you put instead of dV we put dx, then in that case the rho dx will represent the probability of finding a particle within the line element dx at a particular time t. Now the important thing that when we'll say that the wave function is a well-behaved event, because the wave function must show some kind of good behavior. Only in that case we can accept it. Or in other sense, the well-behaved wave function means that acceptable wave function, and acceptable wave functions must satisfy this kind of conditions. Although we have written here u, but this is also valid for our time-dependent wave function psi or t. So the first condition that a well-behaved wave function must satisfy is that this wave function must be finite for all values of position vector. Then it must be continuous. Then the nebula u must be finite for all values of r, and the nebula u must be continuous for all values of r. And if you look at these conditions 1 and 3 here, the first one represents that wave function is finite, and second one means the derivative of u is finite. On the other hand, condition 2 and 4 represents that the wave function is continuous, and 4 represents that the differentiation of wave function is continuous for all values of r. And the last condition is that for if the r tends to plus minus infinity, that is for large values of r, the wave function vanishes, and this actually is nothing condition number 1 actually, which represents that probability is finite for over whole space, or which is known as normalization, to be discussed in the later course of time. Now the condition 1 follows from the fact that a probability is always finite, and we know that probability is related to psi molar square. So if probability is finite, then psi must be finite. Then condition 3 follows from the fact that the current density, probability current density J is finite. We'll take care of J in the later course of time in coming videos. So for the time being, let us think that this J is related with nebula u, and that's why since J is finite, so definitely the nebula u is will be finite, and thus condition 3 is correct. And one must remember that we'll get an equation of continuity for in later course of time, where we'll find del rho by del d plus the divergence of J is equal to 0, which means that if rho is finite, then J is also finite, and if J is finite, then since J is dependent on del nebula u, so nebula is also finite. Now, as we know from the concept of continuity and differentiation, that if nebula is finite, then u must be continuous. So condition number 3 follows. So condition number 2 follows from the fact that condition 3 is correct. So condition 2 is followed from the fact that this nebula is finite. And on the other hand, this would mean that if this quantity is finite, nebula for u is finite, then in that case this nebula will be continuous and the same track. And now when will this will be finite? When we'll discuss more about Schrödinger equation, we'll find that these quantities will be finite when this behavior is finite, that is the potential function is finite, which may be continuous or discontinuous. And so for finite potential, this nebula score is finite, which will be followed from Schrödinger equation. And since nebula score is finite, so it means nebula u is continuous. And also we must remember that this is one of the boundary and continuity conditions. And then regarding this infiniteness of potential, we'll see that in that case this will not be continuous, so we cannot have a well-behaved wave function. So the case of infinite potential is summarily discarded, and we say that the potential is vanished where the wave function is vanished where the potential is infinite. And this is also another theorem on boundary and continuity conditions. So some of the non-acceptable wave functions shown here, which are not satisfying the conditions 1 to 5 here, and this is graphically represented here. So we conclude that the wave function which is responsible for matter wave has no physical meaning, complex quantity. The moduli square bit has a meaning, and if we try to find a physical interpretation of it, we find that it simply represents the probability density. Moduli square bit represents the probability density, and thus it is connected with probability. And when we integrate over the whole space, then that particular integral will give us equal to 1, since the total probability is always equal to 1. So this integration over the whole space will always be equal to 1. And sometimes that some constants will be there, and this constant will be known as normalization constants. In the coming video we'll take care of it. And coming back to conditions for good behavior of a wave function, we see that there are 5 conditions that a well-behaved wave function must satisfy. And also all these things has been followed up from our definitions of physical interpretation of wave function, as well as finiteness of probability, finiteness of probability current density, and also some concepts of limits and differentiation, which we have already familiar with. And also in case of where the potential is infinite, the wave function always vanishes, which will be very useful in the later course of time while discussing the applications of Schrodinger equations. And also we must note that this quantity is finite only when this beer is finite, and this is a thing that will be followed while we're discussing the Schrodinger equations. And these are some figures which represents non-acceptable wave functions which are not satisfying the conditions as given above, like these conditions. So with all this, I am ending up this video. Hope that this video is helpful for you, and thank you very much.